right. So I guess the idea is this: a normal coin account is controlled by a public key and a private key pair, and you have to sign a transaction with your private key. That takes about 200 bytes of information to do that, and that proves that you are the one that actually has the authority to spend out of that account. All right, so encryption in this way is computationally fairly light, but it still actually, asymmetric encryption is actually much heavier than symmetric encryption, so there's some work being done there, especially if there's lots and lots of transactions. On the other hand, these bearer tokens, you create them, and they're controlled by a hash lock. And the way a hash works is you have, say, a random number of 32 bytes or anything you like. You run it through this well-known hash function. It's public information. Hashing is very computationally light, very easy to hash things. So you hash this thing, it gives you what's called a hash digest. The key is that the hash pre-image, the thing that you hashed, will always hash to this. And there are, if you change even one thing in this pre-image, you'll get a completely different hash. So there's no way to really guess what this pre-image is. There's 10 to the 72nd possible pre-images. There's actually an infinity, but that's the equivalence classes of pre-images, 10 to the 77th. So it's computationally impossible to guess. So the only way really to unlock that bearer token is to already know the pre-image. That's the important part of it. All right, so the record is just it's locked with this hash digest. And if I want to spend it, all I have to do is give the pre-image. The blockchain hashes the pre-image, says, yep, that's it. You are the one that knows the pre-image, and that allows you to control that bearer token. And so now the advantage of all this is that, there's an advantage in it's computationally light. It also doesn't take up much information. The pre-image is only 32 bytes. A signature is 200 bytes. So if you're going to try to do microtransactions, it's really good to be able to do them with a very limited set of data as opposed to this much larger set. So anyway, that's the sort of technology behind the way they work.
And in practical terms, what does that mean for the cost of processing a single transaction?
Well, in practical terms, I mean, it's going to create, something like an eighth of, actually probably less than that, probably something like a 20th or much less computational work, and something like an eighth of the bandwidth that's required.
So less than a penny, far less than a penny.
Far less. No, it's already things cost less than 1/100 of a cent. But the concern is not so much the computational cost, but if you're going to do this at scale, if you're actually going to have micropayments that are millions of dollars, but each in the form of a nickel, that's just many transactions. Ethereum does 8 transactions a second, and you can't even begin to do a micropayment on that level. So you have to have a technology that can process 1,000 transactions a second, do it incredibly cheaply, do it quickly, computationally light, low data usage, low bandwidth, and low storage.
And I think those are all the attributes of the protocol that John has designed and we're able to implement to see that this very high throughput is possible on the blockchain. On the Geeq chain, I should say.
Well, this is even higher throughput. Like Visa processes thousands of transactions a second, but you could process millions of transactions.
Well, so Visa does about
much larger number.
Visa does about 50,000 a second, and they can do up to like 250 if they have to. They can probably scale more than that now. So that's all of Visa. That's a lot, right? One instance of our blockchain in our tests can do 1,000 a second, and so we have multiple instances. We have a multi-chain environment. So if one chain gets filled, one chain has already capacity, we can deploy another one, and there's where you get the infinite scalability.
So now you can do any unimaginably large number of transactions a second at an imaginably small fraction of 1/100th of a penny per transaction, and lose all of the friction costs that have slowed down the information blockage that slowed down, say, Ethereum, and the cost blockage that slowed down Visa, and do it both bigger and faster.
Right.